Thanks for coming, guys. Right, so tonight we're going to talk a bit about Scala Futures because we thought let's do a beginner-friendly talk for once and not talk about monads. But then you have a talk after that, and that's going to be, we're going to go back into that realm. Okay, so we're going to be talking about Scala Futures and how you can kind of use them in your code and what kind of patterns you can adopt to kind of make your code nicer, more composable, more readable. And this is the first and last reference to Star Wars in the entire presentation. So if you came for that reason, sorry about that. So what is a future in the first place? So looking at the definition given by the Scala documentation, there's not much we have to add to kind of get an understanding. So a future is an object holding a value which may become available at some point. In some sense, the may gives us the idea that the computation could fail or be successful, and so the value might be there or not, and at some point gives us the idea that the value will be available at some point in time, so in the future. Now, what are futures good for? Just a bunch of examples. Running expensive computations is one of the things you might want to do in a future. And you want to run those computations off the main thread so that your application keep on being responsive. This is actually taken from the Scala Lang website. It's also a terrible example, but it's a contrived example to kind of show you something. The other idea is to get you to retrieve data from maybe a database without blocking your application. And I don't know if any of you are familiar with Slick, but this is an example from the Slick documentation, kind of rearranged, where we are building a query on a coffee table. We're filtering by name, and then we are kind of running our query in an asynchronous fashion with dbrun. aka-HTTP is another library that kind of uses futures quite a lot, and in particular, every time you issue an HTTP request, you get back a future of an HTTP response. And this is another example. And the idea is that you don't have to wait for the response to come back in order to keep on doing what you're doing, to keep on, say, serving your clients. And finally, you can use futures to run concurrent computations. So in this particular instance, say you have a bunch of vectors and a function called length that computes the length of a vector, and you want to compute the length of a collection of vectors. You can simply go with the vectors.map and compute the length, or you can parallelize the computation and just run every single computation in the future. Now, turns out this is not an amazing idea, so you're probably not going to be doing it exactly like this. That's not how you distribute a computation across multiple cores given a collection, but it kind of gives you a sense of what the benefit you might be looking for are. But why would we do that? So why futures? Why not something else? I'm sure you have many other alternatives in mind. Well, I thought about 4 things that they quite like about futures. So having futures in your application make your application responsive, because you can keep on serving client requests or other requests while you're dealing with complex computations, or maybe with some blocking I/O, or maybe with some waiting for a response to come back from an external service. I also like futures quite a lot because it kind of they allow you to kind of isolate errors in your application and deal with them in a very controlled fashion. And we're going to see some of that in a few slides. It's definitely something you use for performance. You want to fully utilize the power of your cores, and you know that you can't just say on the main thread in order to do that. And finally, because futures have an API which is strongly typed, as opposed to actors, for instance, they kind of make your code easily composable. So composability, maintainability are, in my opinion, one of the good benefits you get from using futures. Right, but how does it work? And this is a bunch of slides you've never seen before, because nobody ever gets bothered with actually talking about this. So we're going to be talking about what happens to futures and code inside that. This is all kind of not super kind of specific or detailed. It's just to give you kind of an idea of what goes on. So we have a bunch of futures. We can think of each one of these as a task. And on the other side, we have an execution context. An execution context is going to take care of actually running these tasks on our resources, on our cores. Now, why haven't we seen execution contexts so far? Well, because most of the time, execution contexts are passed implicitly into our method calls, both through the Future API or through Slick or through the HTTP interface. But you can actually have a say in that. But we're not going to be talking about that too much. Now, inside the execution context. Right, so we're just going to give you, go for one possible model for an execution context. We have a shared queue of tasks. So that's what happened to all the the blocks of code coming from our different futures. And we have a thread pool. To keep things easy, we're going for a fixed thread pool. So we have a given number of threads, and those are the ones we're going to work with. And then on the bottom left, you have a scheduler. The scheduler is the one in charge for deciding which thread gets time to run a particular task. So assuming the scheduler is quite either busy with other things or we only have 2 cores, you can see the kind of scenario where thread 1 and 3 get some time to run. They get a couple of tasks, one task each, and they start running it. Then the scheduler decides that it's time for thread number 3 to give up some of its time and give some time to thread 2 to get a task and run it. And say that thread 2 is actually very quick and it completes the task. And off we go, it gets another task. The scheduler decides that thread 2 needs to wait for a bit. Thread 3 starts working again, and then in the meantime, thread 1 finishes processing task A, and that's it. And on like this. So this is the execution model we're looking at, more or less. Now, if something you might have gotten from this example is the fact that even if you have a very large number of threads, the number of parallel computation you're running always depends on the underlying architecture. In particular, you're limited by number of cores, and also in case there are other execution contexts across your application, you're going to be sharing those resources, so cores, with those execution contexts as well. So the scheduler will have to find the time to make your thread run. And that's quite challenging concept in complex application, as some of you might know. But again, we're not going to spend too much time on this today. OK, so how do we use futures in our application? Right, so let's just go through the basic of the API. For each is something you definitely, well, you might have heard of, definitely for collections. It's a method call that that kind of injects the value underlying the future into our block, and then we can do something with that value. In particular, in this case, we can do something if a cycle was found in our graph. Otherwise, we just print something else. Now, a particular thing about for each is that it returns a future of unit. So it kind of discards the value that was processed in the previous computation. And that's not always what you want. That's why we have map. So map allows you to process the underlying value, but also returns the return type is going to be whatever the type of the inner computation is. So in this case, we detect any cycle in G, and then if we don't find any cycle, then we proceed with the computation of the topological ordering for the graph. And depending on the result, we return a future of option of sequence of int. Ugly signature, contrived example, but you get the idea. Now, another kind of method that we find really interesting and we kind of use quite a lot in our code is and then. This is not one of the most well-known bits of the API, in my opinion, because you see people doing weird stuff all the time, and this actually helps a lot. So what and then does is it allows you to do side effect on either the failure or the success wrapped into the future without affecting the return type of the expression you're manipulating. So this means when you run find coloring upper bound, you get a future of an integer running, and then on the top of that will not affect the return type, will not affect the inner value. So after the and then, we can map, and we still have the upper bound, and we can just call coloring with that upper bound. Flat map is possibly the last bit of the API we're going to look into. It allows you, it kind of expresses the dependency between different futures. So looking at this code, you can see once you start having futures across your application, you usually start defining functions or methods that return futures. And then you end up having situations where you get a future, then you map something and receive another future, and then you end up having a future of something. But most of the time you don't want to work with that, you just want to work with the inner value. So that's why we have flat map. And what it does, it's basically kind of flattening the structure of the futures and kind of even though you have dependent computation, it kind of keeps the structure very flat, so you can always get fast access to the underlying value you're interested in. Oh, I was lying. So last bit of API, handling failures. We can use recover. We're going to see this in action in a bit. But yeah, so in case anything went wrong with the computation, you know that you can handle an exception, then depending on that, do something in case you can recover the computation. In this particular case, we're computing the upper bound for the coloring of a graph. In case something goes wrong, we're just going to go with an upper bound, which is known to be all right, which is the size of the graph. And then we just map the upper bound into the coloring function. And that just works fine. Cool. So this is the API. But what the API we kind of like. But what if I have old code written with other bits of the API or like things that could be maybe refactored? Well, so let's just go through some of the patterns we've seen most of the time in our code, and we can try to fix. One thing that you might see quite often is the fact that you instantiate a future on a value that is already known at runtime. So you don't really need to wrap the value into a future, but you feel like you should do it just for signature purposes in order to comply with the signature. This is a classic. Now, this is a very bad idea, because wrapping anything into a future constructor, into the apply method, will actually spawn that mechanism that we saw earlier, where a task will be created, will be passed to the execution context, and then the execution context will have to give some time to threads to run that particular task, even if it's a already computed value. So you should avoid doing that. That's just making your application slower. What you can use is .successful. That's just going to return a future without allocating any, without having to allocate any task to add any task to the execution context. And that's quite neat. So successful. Right. And then is another one that, as we were saying, is not really well known in my opinion. So a lot of time, you can tell me if it's something you've seen already. You end up seeing this kind of pattern on map, which is terrible and ugly and, yeah, hard to relate with. So we get something from a storage, then we map the result, but we would like to log something before going on. So what we do is we log something, but then we also want to return the previous result. So we go, oh, log and then result, which is kind of a good code smell that shows you that maybe something could be improved. And then is exactly what you need in these circumstances. So you just go, and then wants a partial function, so you can forget about whatever you don't want to care about, and just work with the success, log something, and then the return object will be whatever was returned by the previous call. And then you just map transform, and that just works fine. And then. And finally, transform. Transform and transform with are two bits of the API that have changed quite a lot between 2.12 and 2.11 and 2.12. So in case you're not using 2.12, this might look a bit wrong, and that's because this is 2.12 only. So 2.12 gives us a very nice API for transforming futures into something else. So suppose you have a sequence of calls, like in this case, you have get color upper bound, and then you flat map, and then you recover. Now, the question is, what are you recovering? Because a failure could have happened in the first bit, a failure could have happened in the call of coloring, but by recovering, you don't know what you're dealing with, right? And that's actually fine. I know there's a lot of talking about, oh yeah, only worry about the epi path. Yeah, but that's not how it works. You actually want to know what went wrong. At least you want to log something. Maybe you're not going to act on that, but you're definitely going to do some side effect. You're going to log something. You want to know what went wrong. which are we handling? So transform. So transform takes a, I think it's actually wants a function from a trie of your type t to a future. So you can actually kind of transform your feature into something else, and this is exactly what you want. It's a kind of more of a fine-grained control over possible failures. And then if you want to recover at the end of it, that's a different story. Finally, for comprehension, kind of gave the title to this presentation. So oftentimes you find yourself with this particular pattern, kind of a staircase to hell or something, and it can go as deep as you like. And you know you can actually avoid this as long as you're dealing with futures all the way through, which is probably or like mostly the case, without going to weird cats or like Scala Z API for dealing with future and options. So this is what you do. You can just turn that ugly bit of code into a very nice, very kind of neat for comprehension. And this is what it looks like. So you go one computation at a time. The only thing to remember with this kind of approach is the fact that computations are dependent one from the other. So you're only going to start running coloring after you get the result from get color upper bound. So these two are not going to be running in parallel. And this is usually what you want when you take this approach, but sometimes you actually want to run things in parallel. And in those particular cases, you should just initialize your feature outside of the for comprehension and then pass them inside the for comprehension. So they are running already, and just going to wait for their completion and then go on. Nice. Looks like I made this like 5 minutes ago, right? That's exactly what happened. So, right. So another thing I wanted to talk about today is the relationship between actors and futures. Mostly because I think there's a lot of misconceptions around how actors and futures operate and what it means to run things in the, on the dispatcher execution context and so on. So we're going to go through kind of a simple example. There's going to be a lot of code, and I'm sorry about that, but please bear with me. So I kind of came up with this scenario. You have actor A that talks to a user profile actor inside your ACK application. And outside of this nice application, you have a user profile API that you can use to retrieve information about a user. Now, actor A issues a call to the user sends a message to the user profile actor, get user profile. User profile actor sends an HTTP request to the user profile API. The API responds, and then we send a message back to actor A. Now, how do we usually model this in an ACK application? There are many ways of doing this. The simplest one is possibly by using the ask pattern, which is one of the most hated patterns in ACK for some reason. And we're going to use that just because I like it. Now, why is this kind of application interesting for your everyday work? Well, because oftentimes we have an actor talking to the outside world, and what we would like to do is, after the first request has gone through, we would like to kind of use these kind of actor, intermediate actor as a cache between our external service and our application. And so we would like to kind of short circuit, and if we have the response, the result already needed for actor A, we just send the response back. Now, you might think that implementing a cache in ACK is simple, and it is. There are some kind of things to be aware of. Right. So actor A asks about the user profile to the user profile actor. What does the user profile actor looks like? There are many ways of getting this wrong. So receive log for the user profile actor. We get a get user profile message. We look into our cache, which is a nice var. We look into our cache. We either find a profile and send it back to the sender, or in case we didn't find anything, we fetch the user profile from the API. And then once we get the profile, we update the cache and then send the message back to the sender. Now, what's wrong with this? Right. So the first thing one learns while reading through the documentation of ACK is the fact that when you play with actors, you should be wary of referencing closing over the context of the actor itself. What this means is that you shouldn't be calling functions that are valid outside of the future context as if you were in the actor context. So sender doesn't have the meaning you think it has. In particular, what could be happening is that when you call the function, when you call the sender function, you get another sender, which is not the sender, the sender that sent the message in the first place. So we live in two different worlds. Once we are in the future context, whatever we used to know, all the kind of the atomic updates and kind of all the niceties of working in an actor kind of fall apart. So that's not true anymore. So an easy fix for this particular situation is to just go with an approach like this. Now there is still an issue here, but what we're doing here, like one fix at a time, is we're defining a sender, like a ref outside of the future context, and then we just use that. So we are closing over a variable which is statically defined. So we know that that's the right sender at this point. Now there's still a bit of an issue, right? One thing is that we're modifying cache inside the future context, which is not great. But the other thing is that for each request, if, say, 4 actors ask for a user with ID 1, we're going to issue 4 requests and not wait for the first one to come back to us. So there's a kind of a bit of a more complex implementation where we try to kind of address this. So we have a bunch of subscribers. So if the profile is there, then we just return it. If the profile is not there, if we are the first one asking for a particular user ID profile, then we fetch. If that's not the case, then we just append a subscriber to our subscribers for that particular user ID. Is there any issue with this? Yes?
It's going to be racing.
Sorry?
Is it not going to be racing?
Yes, it's going to be racing. Where does the race condition come from? Well, because we are modifying variables inside the future context, what could be happening is that in a different thread, a task is being run at the level of the actor where we're making this particular change, and we're basically maybe appending something to the subscriber. Remember that this is a destructive assignment, so we're basically replacing a subscriber's object with a new one. And what could happen is that you have 2 threads concurrently running, well, running in parallel. One is running this line, and one is running this line. How is that possible? Great question. It's possible because once you issue the fetch request, so when you fetch, this fetch is a non-blocking request, HTTP request. Wait. So akka guarantees that once you're done processing this message, you have this future hanging there, but you're still going to process messages coming in. So you're not blocking, waiting for the response to come back to the actor. So what's going to happen is that the actor is going to keep on processing messages. In the meantime, in a callback fashion, as soon as the request comes back, you're going to be running this particular bit of code, possibly in the dispatcher itself, on the dispatcher execution context, but that's a big issue. So again, what are the effects of this? Well, the effects are the fact that you might lose subscribers or lose cache elements and have to issue the request again. But it's like the effects are catastrophic. So what's the rule of thumb in these particular situations? Just don't do any side effects on the actor variables inside future context. None. What's the right way of approaching this kind of problem? Well, one possible solution is to do as little as you can with the future. So you issue an HTTP request to the profile API, you wrap it into a fetched user profile case class, and then as soon as you get it, you pipe it to self. Now, as soon as we pipe it to self, we're going to get back into the guarantees we have for all the actor processing operations, which is that everything is atomic, that we can assume that our execution is only in one place at any given time, and everything goes back into the stuff we know how to reason about. So in this particular case, we pipe to self, which means the message will be enqueued in the message queue for the actor. As soon as we start processing that particular message, that's the only thing that is happening in the actor at all. And so we can go here, made side effects on the cache, made side effect on the subscribers, in total safety. This is nice. It also kind of opens to something else. When you pipe to, the implementation of pipe 2 does a nice thing. If the future you're piping is a success, then everything is going to be all right. You're just going to pipe it to self, and it's going to be the particular type of object you expect. In this particular case, a fetch user profile. If there was a failure there, then you're going to have to handle a status failure. A status failure message is actually a nice message to handle because it contains a lot of information about what went wrong. And again, think about the happy path works only in talks. You actually want to know when something broke, and you need to take care of those situations. So you actually do want to handle these scenarios. And the pipe 2 pattern is actually forcing you to think about those scenarios too. Whereas if you were to just go and send messages without waiting for a response and go like, well, at some point I'm going to get a response, you're just missing out on a set of possible failures that you should really think about. Right. So to recap, it's going to be super, super fast. This is your application with features. It's fast, it's responsive, it's awesome. These are your features. They're composable with their API. They lead to writing maintainable code, and they're available in many colors. I guess that's the slide I've got. That's, yeah. So this is you without features. Better handling. Should have used Scala Futures. And finally, the takeaway message. In your app applications, if actors are your ingredients, remember you also need, for a good app application, you also need ask and pipe 2. That's it.